All right, so just to review, the most important part of the unit and the name of the unit, if you guys notice, is that the name of the unit is forces of attraction between, and intramolecular forces are basically the forces inside of the molecule. So think of like covalent. Okay, so just to reiterate, London dispersion forces, weakest intermolecular force. The higher the molar mass of a molecule, the more it is affected by these London dispersion forces. And it's caused by these instantaneous dipoles. Okay, so if we were going to compare them, so this might be on your exam depending on the version of the test you have. It might ask you, for example, what experiences greater intermolecular or London dispersion forces. It'll give you something like CH4 versus like C8H12. Okay, and which one is going to experience more, the left or the right? The right, and it's because it is bigger. There are more electrons, so they'll congregate to one side and they'll kind of stay there for a longer period of time. Okay, and again, it's not inside one molecule, it's between a lot of these molecules. Okay. All right, so that is the first intermolecular force, the weakest one. The second one that you guys should have watched in the video are called dipole-dipole forces. You guys might have heard this. This one's easy to remember. My first name is Paul, and I know you all hate me, so dipole-dipole. Okay, so if you write dipole-dipole on the test, I'll take it. And this is the middle, the second intermolecular force. And this is caused, and this is only experienced by polar molecules. Okay? Just like how I probably make you polar in this class. Set you off edge. All right, dipole-dipole. So again, this is only in polar molecules. So we talked about polar versus non-polar at the beginning of this unit. So for example, CH4, I'm just going to draw a picture. You guys don't need to draw this. And again, this is all being recorded. If you notice, there's no part of the molecule that has more electronegative or electron pairs, right? And so this is nonpolar. And so if it is nonpolar, you cannot experience dipole-dipole forces because there's no specific side that is polar. However, let's say something like HF, right? We know that F is the most electronegative element. So there's going to be a polarity that goes towards that. This side is going to be partially negative. This side is partially positive. And so this experiences dipole-dipole forces because what's going to happen is it's going to line up with other HF molecules. Since this is negative, this side is partially positive, it's going to experience an attraction between the H and the F of different HF molecules. So that's a dipole-dipole force. Okay, so again, this is only experienced by polar molecules. If a molecule is not polar, it can only experience London dispersion forces. Okay, so that's a big hint for your exam actually, because there's going to be questions that ask you to list what are all the intermolecular forces the molecule experiences. If it's nonpolar, it's just London dispersion. If it's polar, you got dipole-dipole and London dispersion. Okay. All right. The third and the last one is called hydrogen bonding. Okay, and hydrogen bonding is like a super version of dipole-dipole. Okay, it is only experienced by polar. So again, it's only polar molecules. However, it is a very specific type of dipole-dipole. You can only molecules that have that can experience this can only occur if there is an HF bond, an HO bond, and an HN bond. That's it. Nothing else can experience hydrogen bonding. Okay, so this is really easy because if you look at the periodic table, NOF is next to each other. So NOF. Okay, only NOF can experience this. Yeah.
There's like an H to like F or something that's like not polar.
H and F will always be a polar bond, yeah.
Can one of those things happen?
No. This is so this is kind of going in terms of polarity. So this one, everyone, like every molecule experiences London dispersion because they all have electrons. And then this, so nonpolar can have this too, but once you get to dipole, only polar. So after this, no more nonpolar. So these guys are polar only. Does that answer your question? Okay. All right, so HF is pretty much the same thing as dipole. Why did I erase that? That was dumb. So it's the same thing as dipole. It's the attraction between two molecules that are polar, but it can only happen if there is a connection between H and F. And the reason why is because F, O, and N are so electronegative, they pretty much take all the electrons, and so it just becomes super duper partially positive, super duper partially negative, and it makes a very strong intermolecular force. Another example, and this is the one that you might see a lot on the AP test, is with water. You see how the H is bonded to the O, right? So this will create a partial positive on this side, partial negative on this side, and if it sees another H2O molecule, same thing. This is going to create a intermolecular force, and this is what we call a hydrogen bond. Okay, but this does not work with other polar bonds. So for example, if you have like HS, it's not going to have the same. This is not a hydrogen bond. This is dipole only. Okay, this is dipole. This is not H bonding. Yeah.
So if one was hydrogen bond, it would write all three.
Correct. Exactly. Yeah. So water experiences London dispersion, dipole, and hydrogen bonding. HS experiences only London dispersion and dipole, and something like CH4 that's nonpolar, only London dispersion. Yeah, great way to break that down. Okay. All right. So that was like the most important part of last class. If you want to look at the chart that was in, that was on the workbook, it's on page, what is this? What page is this? 23. It kind of gives you like a breakdown, and it also gives you the strength of these intermolecular forces. Okay. Everybody good? Okay. Let's talk real quick about the geometry chart, because I told you there are things you need to memorize, and you don't need to memorize all of them, but I'm going to tell you what you need to know for your test and for the AP test. Okay, so if you have your geometry chart, this will be a good time to take it out so you can make some notes. Okay, so hopefully you're able to use the geometry chart in order to find shapes. If you're still having trouble with that, come see me, because you're going to need some help with that. But you need to know basically the first 6. Where did my pen go? Am I tripping? There it is. All right, you need to know the first 6. Linear, trigonal planar, angular, tetrahedral, trigonal pyramidal, and angular. Okay, now, your textbook, I think, says bent, so you can do bent. I call it bent. So bent or angular, they both work. But you need to know these shapes. And so if I give you a molecule that's any of these 6, you need to be able to identify them. Okay? And we got some examples right here. If you want to draw them so you can see what they look like, that's totally fine. Okay, but your test is guaranteed to have a couple of these, and the AP test is pretty much going to expect you to know these. The other ones on the bottom, they're nice to know. If you can find it with a chart, great, but I'm not going to expect you to memorize those ones. All right. So the first 6. You do not need to memorize the bond angles, but it's actually pretty self-explanatory. Like if you have a linear, a straight one, that's 180, right? If you have this one, it's like a triangle, that's 120. 360 divided by 3 is 120. And then the only one you really need to know is the 109.5. And then these ones, you just need to know that because there's lone pairs, it's going to push these bonds down more, so it's less than 109.5. Same thing with the angular. All right, so for the review, we're going to look at 2 different processes, and then we're going to talk about them and the forces that are involved. So let's start with process 1. I'm just going to talk about what's going on, and then after that, I'm going to have you guys try A, B, C, and D, okay? So for the processes, let's just break them down. It tells you process 1, liquid NH3 vaporizes to gaseous NH3. So basically in this situation, I'm just going to draw circles. Let's say these are NH3 molecules, When they're liquid form, they're like stuck together, right? They're moving, but they're stuck together. It vaporizes, and so what's going to happen is they start separating and becoming their own NH3 gaseous molecules. Okay, that's process 1. And then process 2, it tells you have NH3, and what's happening? The nitrogens and the hydrogens are separating. So let's take a look at process 2 first, because I think this is easier. What is being broken in process 2? The bonds. What type of bond? What's the name of the bond being broken? Not H bonds. What was that? Yeah, covalent, because the molecule is breaking apart, right? What keeps the molecule together? Covalent bonds. So the answer to number 2, what is being overcome? The covalent bonds. The molecule itself is breaking apart. So when the molecule separates, the covalent bonds separate. What's up?
I just want to show you a funny picture.
Okay, you want to show me a funny picture? All right, you guys can try A while I look at a funny picture. So for process 1, the intermolecular forces are being broken because NH3 is still staying together as a molecule, so covalent bonds aren't breaking. It's just intermolecular. And so you just need to identify what intermolecular NH3 experiences. So what's one that it experiences? Oh, God.
Hydrogen bonding.
Yeah, hydrogen bonding. Hydrogen bonding, because if you look at NH3, what type of bond does it have? An NH bond. So hydrogen bonding. And we said earlier, if it experiences hydrogen bonding, it experiences the rest of them as well. So dipole, dipole, Mr. O, Mr. O. And everybody experiences London dispersion forces. What's up? Yes, so the answer is 2. And the reason why it is 2 is because covalent bonds take a lot more energy to break than intermolecular forces. Okay? Easy way to think about this is, let's say this is you and your significant other. Okay, you are 2 different molecules holding hands. Okay? Now, it is a lot easier to separate your hands from one another, your intermolecular forces, than it is for me to rip out your arm. That is intramolecular, right? So think of it that way. It is easier to separate holding hands, intermolecular, than to rip out the arm. Okay? Yeah. See, now you'll never forget that. All right. So D. So the question is asking, do you agree with this statement right here? So the statement is, when ammonia boils, the forces keeping the nitrogen and hydrogen atoms together are broken. What do you think? Agree or disagree? Disagree. It is disagree, because when you are boiling, what are you doing? You're separating the molecules. The statement is saying you're breaking the molecule apart. You're separating them, which is not what is happening. Just remember, boiling is always separating the intermolecular forces, not the intramolecular. Okay? So the answer for that is disagree, and you would say boiling breaks apart the intermolecular forces, not the intramolecular. Okay? So B tells you that this chlorine-carbon bond right here is 178 picometers. And then it's asking, is the carbon to bromine bond in CBr4 expected to be greater, less, or equal to this value? Anyone take a shot at it? Yeah. You put less than. Why did you put less than? Yeah, so that is true. It is less electronegative. So if I drew carbon and bromine, it is less electronegative with the bromine, right? So that means that bromine is going to share the electrons more. Now, if you think about it, if this is more electronegative and is pulling the electrons closer to itself, is that going to lengthen or shorten the bond? It's going to shorten the bond because it's holding it tighter. It's bringing the electrons in tighter. So the answer will be that it is greater. Carbon-bromine will be greater, and because of bromine is less electronegative. Also, another thing you think about is the number of shells. If you look at chlorine, chlorine has 3 shells, right? So if you drew it, it would be 3 shells, and electrons are shared right here with the carbon, which is in the second shell. But bromine has how many shells? It has 4. versus the chlorine's 3. So they are shared between 2 and 3 here, 2 and 4 here. Bromine's just bigger, so it's going to have a longer bond length. Okay, so those are the two explanations that you can give. Okay, bromine is less electronegative, which lengthens the bond. Bromine is also bigger, so it's going to lengthen the bond. Yeah.
So it's fine, just like the shells.
Exactly. Yeah, I think shells is the easier way to look at this. Yeah. Yeah.
So can you argue that there were electronegativity?
Yeah, both will work. Yeah. You don't need to provide both, just one. Great question. All right, this is very similar to part C, where it's talking about a different molecule now. So carbon-sulfur bond is, it tells you the bond enthalpy now. So now they're going from length. So this question was talking about bond length, and now it's talking about bond energy. Okay, so we need to keep that correlation in mind. It tells you carbon-sulfur is 575 kilojoules. So if you have a carbon, this is going to be a double bond. It's telling you that it is 577 kilojoules per mole to break it. And then it tells you the carbon-selenium bond, and it's basically asking, is it greater, less than, or equal to? So same thing here. We're going to look at the periodic table because I know selenium, we don't use it as much. So if you compare sulfur and selenium, let's start with we can do electronegativity or size, okay? Let's do electronegativity. Which one is more electronegative? Sulfur is more electronegative than selenium. Let's go with size. Is sulfur bigger or smaller than selenium? Yeah, less shell, so it is smaller. Okay, it is smaller than selenium. So the question is asking, which one takes more energy to break? So bond energy refers to breaking. So which one requires more energy? So if you think about it, is a shorter bond or a longer bond easier to break? Longer is easier to break. Okay, longer is easier to break. So think of it this way. If you have a friend with very short T-Rex arms, is that easier to break than a friend with very long Victor Wembanyama arms? This one is probably easier to break, right? Because it's longer. It's more, if you took physics, you know, the arm length, and yeah, anyway. So this is easier to break. So if you look at selenium, the selenium carbon bond is longer, right? And so the selenium carbon bond is going to have a lower bond energy. Okay? So that's the correlation that this question is looking for. Do you know the relationship between bond length and bond energy? Basically, the key here is if you increase the length of the bond, you're going to decrease the bond energy. It is easier to break. So let me just draw these structures for you real quick. I'm going to draw it 3D. If you did it 2D, that's totally fine. But NH3 is going to look like this. You got N as a central atom. You got lone pairs. And then you got hydrogens attached to it. Everybody good? Okay. Again, if you did it 2D, that's fine as well. All right, NH4 is going to have everything connected to nitrogen. So it's going to look something like this right here. And if you forgot on the quiz to put brackets, I think I was pretty lenient with it. Although I shouldn't have been. Okay. So everybody go to the structures. Let's talk about the bond angle. So if you look at the question, it's asking you compare the bond angles of NH3 and NH4+. Now, which one of these do we know the exact bond angle for? NH4+. Remember, this is a tetrahedral. So this is exactly 109.5 degrees. Okay, and the structure is tetrahedral. So if you want to fact check me with your geometry sheet, you can. But this one right here, if you look at NH3, you guys see how there's lone pairs, right? Now, if you remember, electrons are the most the most negative thing you can have, right? So these are super negative. And so what they do is they start to repel the electrons in these covalent bonds. So it actually pushes the single bonds down away from the lone pairs, just because electrons are just negative. They're just like, that's as negative as you can get. So it pushes these down, so it actually makes this bond length right here less than 109.5. So this is something that you're going to have to keep in mind. It will be on your test, just a heads up. And so NH3, the shape is trigonal pyramidal. Okay, and this one right here is going to have a smaller bond angle. So if you have your methane molecules at home, I have them right here if you can look at it. This is NH4+, it's tetrahedral, and this would be NH3. What's going to happen is the lone pairs up here basically push the single bonds down. So basically what it does is just pushes them all down like this, and it makes it less than 109.5. Yeah. Is it not on Canvas? Oh, on the exam? No, you will not. You need to know the 6 that I mentioned. Yeah, so get some flashcards. When you're taking a dump, just... That's how I memorized it in college. Yeah, I memorized a lot of chem stuff while taking a dump. Yo, because it's like 15, 20 minutes you're there. Might as well do something. Okay, my bad. You guys have better bowel movement than me. Way to flex your digestive system. All right. Any questions on ENF? Yeah. I don't know. Some nerd came up with these names. I literally... Okay, if it was me, I would have called this tripod. Tripod, no camera. So easy, yeah. Anyway. Yeah. All right. Let's move on. We're not gonna do any of this. All right. Let's try 4. I'm gonna have you try 4 on your own. So if you notice, a lot of these questions are asking you to compare things, right? So that's pretty much what you're gonna be doing here. For part A, you just need to identify which one has a higher boiling point. Just write the name or the symbol for the molecule. And then for part B, explain your reasoning. Again, keep it concise. I don't like reading essays. 1 or 2 sentences max. Okay? On the test, if you write a lot, I'm not going to penalize you, but I'm going to grade a bit harder. Okay? So just 1 or 2 sentences max for your explanation. You don't need a lot of explaining. All right, so the answer is HF. Okay, so for part A, we're just going to write HF. So let's talk about why. This has to do, God bless you. So boiling point always has to do with the intermolecular forces. So because what you're doing when you're boiling, God bless you, is you're taking the liquid particles, right? And you are turning them into gas particles. So what you're doing is you're separating the forces, God bless you, keeping them together. So we just need to figure out what intermolecular forces there are. If it has stronger intermolecular forces, it's going to be harder to boil it, right? To vaporize it. So if you look at HF, what intermolecular forces does HF experience? H bonds, which means they have the rest of them as well, right? It has dipole, and it also has London dispersion forces. If you look at neon, though, what's the intermolecular forces neon experiences? Yeah, only London dispersion, because neon is a noble gas. It is nonpolar. So that is your reasoning. You would basically say HF experiences, so has H bonds, dipole, and London dispersion forces, which means it has stronger intermolecular forces than neon. Therefore, it has a higher boiling point because it requires more energy to vaporize it. Something like that. So you're gonna refer to the intermolecular forces HF has. You have to talk about the intermolecular forces that neon has, and you need to make the assessment that this one has stronger intermolecular forces. So you need to talk about those things. Okay, so remember, always give all the information the question is asking for. And so you're talking about boiling points, so you got to talk about boiling points. Yeah. Yeah. I guess you could say HF experiences stronger intermolecular forces than neon. I would recommend listing it just to show that you know what you're talking about. Yeah. Because if you only say hydrogen bonds, the reader the reader might assume you know the other ones, but the reader could also assume, oh, this person only knows the hydrogen bond. So you just don't want to give the reader room to guess. Yeah.
You're so clever.
It has to, H has to be bonded to one of the FON. Yeah. So for example, let me just think. An example I might think of is, hold up, my mouse just died. Would be something like if you have like CHO, or sorry, CH2O. This one has H and O, but if you drew it out, it looks like this. So this does not have hydrogen bonding because the hydrogen is connected to the carbon, right? And so you have to be aware of it. So yeah, generally I guess you can make the assumption, but there are examples that don't work that way. Yeah, great question though. Any other questions? Okay. All right, we did a question very similar to 5 on the lecture, so we're gonna skip this one as well. I'm just trying to get through as many as we can. Number 6 is very similar. I'm gonna briefly go over this with you. This is a different way of writing the same question we looked at. It says, actually, it's a little different. I'm gonna have to try 6. My bad. So try 6. It tells you that at standard conditions, STP, ethane is a gas, hexane is a liquid. Explain why. I'll give you about 2 minutes to do that. All right, guys. So for 6, it tells you basically what you have. It tells you that ethane is a gas, and hexane is a liquid. So what this should automatically tell you, why is my pen dead? Okay. What this should automatically tell you is that which one has greater intermolecular forces, ethane or hexane? Hexane. This one has stronger intermolecular forces. Sorry, I have to write with my mouse right now because my pen just died, but this one has stronger intermolecular forces because it is a liquid at the same temperature and pressure. Everybody understand that? Okay, so what we need to do now is identify what are these intermolecular forces. So if you look at ethane, what is the intermolecular force that ethane experiences? Yeah, LDF, London dispersion forces. Now, just because you're using the acronym, for our test, you can write LDF, you can write DP for dipole-dipole, you can write H bonding. But for the AP test, don't do that. Okay, yeah, again, don't give the grader room to grade. With me, I'll take it just because I know what you're talking about. It's the acronyms we're using, but for the actual exam, just be more, don't use those acronyms, okay? Okay, so London dispersion. What about hexane? What does hexane experience? Yeah, same thing. Does it experience anything else? No, it is non-polar. If you don't know, any hydrocarbon, anything made out of hydrogen and carbon only, it'll always be non-polar. Yeah. What's up? Okay. So that means that they both only have London dispersion forces, but hexane is stronger. Why does hexane have stronger London dispersion forces? Yeah, what's up? Exactly. That's it. You can say bigger, larger, higher molar mass. Either or any of those answers will be fine. That is the explanation. So you would just basically say that ethane and hexane both only experience London dispersion, but hexane, since it is bigger, experiences stronger London dispersion forces. Okay? All right, so we're going to do number 7. I want you to try A, B, and C on your own. I know these structures look kind of complicated and large, but if you want, just pull it up on your Chromebook so you can look at it a little better. A and B are pretty simple. It's basically what we've been doing. Just list the intermolecular forces they have. And then C is asking you why one of them is soluble in water and one is not. So think about it. Take a couple minutes. I'll give you about 4 minutes to do this, and then we'll go over it and then move on. All right, so I'm going to go through this really fast just for the sake of time. If you look at glucose right here, the first thing you should see is there is an oxygen-hydrogen covalent bond, right? Which means this is going to have all of them. It's going to have H bonds, it's going to have dipole-dipole, and it's going to have London dispersion forces. If you look at cyclohexane, though, what do you notice about this? This is only carbon and hydrogen, right? This is a hydrocarbon. This means it's non-polar, which means the only intermolecular force it has is London dispersion forces. Okay, so that's the first thing that you want to identify on that. Everybody good? Okay. Now, it's saying that glucose is soluble in water, but cyclohexane is not, and it's asking you to explain. Now, I mentioned it very briefly in the video, so you might have missed it if you were kind of not paying attention, but there's a phrase that has to do with solubility with this unit, and it's pretty important, so if you don't know it, jot it down, but it's that like dissolves like. And what that means is polar stuff dissolves in polar stuff, non-polar stuff dissolves in non-polar, but they don't. So easy way to think about this is oil and water don't mix, right? And it's because water is polar, oil is non-polar, so they don't dissolve in each other. Okay? So glucose is soluble in water because it is polar. You guys see these hydrogen potentials for hydrogen bonds. So if a water molecule comes up to it, what's going to happen is that the O in the water is going to form a hydrogen bond with the H in the glucose. And that, but if you look at cyclohexane, there's nowhere for any polar intermolecular forces to act, and so that's the reason why. So for your answer, you can literally just write like dissolves like and kind of explain it. Polar dissolves in polar, and glucose and water are polar, but cyclohexane is non-polar. That's a total fine explanation. But keep that in mind, like dissolves like. Polar stuff dissolves in polar, but non-polar does not dissolve in water, polar stuff. Okay? Alrighty, we are getting to the end of the review. So I think we can skip this. This is very similar. Find the intermolecular. So if you guys notice for the review, a lot of it is just find the intermolecular forces, compare them. So here it's asking which one has a higher boiling point. So same thing that we've been doing. This one is 4 mole charge. This one, you can look at the equation for that. And this is enthalpy of the reaction. You would have to draw the structure and do the thing and just subtract it. All right. The one that I really wanted to do was this problem because it is from last year's AP exam. So you get a good idea of some of the intermolecular force questions you'll see and the level of difficulty. So just to kind of simulate what happens on the AP test, I'm going to shut up for about 7 minutes, and I want you to try this on your own. It's only a 2-part question, but see if you can interpret the question on your own. That way you can see, can I understand what types of phrases, what types of questions on the AP test, and see if you guys can do this last question on your own. I'll give you about 7-8 minutes, and then we will go over it together. All right, so I counted up the valence electrons for you just to save time. Should be pretty easy. NO2 is 17, and it's an odd number, and that's the reason why we have a electron by itself right here. NO2 plus, however, is 16. This is 16. So just to make it fast, it's going to be a double bond. And you have to draw the lone pairs for this one. So you're going to have two sets of lone pairs, 4 electrons on the oxygens. Everybody good? Everybody not good? So 16 electrons. You're going to have to single bond them at least. So 2, 4. You got to give everybody 8. So 6, 8. Nitrogen is happy. And then 10, 12, 14, 16. That's how you get the oxygens to 8 as well. So that is number 1. So let's just draw the Lewis structure in this box. That's all you have to do. Now, for 2, you need to evaluate a statement. Basically, the statement is the bond angles in NO2 and NO2 plus are different from each other. So let's start with NO2 plus because this is the one that's really easy. What is the bond angle here? Yeah, 180. It's just linear, right? It's just a straight line. So this is 180 degrees because it is linear. But if you take a look at NO2, is this linear?
No.
No, why not?
Because there's a lone pair.
Yeah, not a lone pair alone, yeah. But great idea. So electron will push these bonds ever so slightly down. And so this will be very slightly, less than 180 degrees. Okay, and that would be your answer. That the lone electron, the one electron, because it is negative, will push these single bonds down closer to each other, making it a little less than 180.